Hello and welcome to day 5. We are in the last day for Unit 8. We're going to be looking at some more definite integrals and some long division, which includes some completing the square. Exciting stuff. So let's get right into it. We have the integral from 0 to 2 of x times x squared plus 1 raised to the 5th. It's not just a normal integral, so therefore we have to use our only other method that we know how, which is u sub. So as I go along, you can write along with me here. So we're going to get u to equal x squared plus 1 du to equal 2x dx. And so du over 2 equals x dx. And so we'll get the integral from 0 to 2 of 1/2 out in front of u to the 5th du. And then let's just go and solve it. u to the 6 over 6 from 0 to 2. You can pull that 1/6 out, so I'll get 1/12 u, which was x squared plus 1, so we'll plug that back in from 0 to 2. And now we'll evaluate the definite integral, so we'll get 2 squared plus 1. Oh, we gotta make sure that's raised to the 6th there. Minus 0 squared plus 1. 1/12. Let's see here. 5 to the 6 minus 1 to the 6. And that number is 15,625 minus 1. And with that, we'll get 1. That entire thing is equal to 1,302. And so all I did there was evaluate it. Long, but not that difficult. But I want to show you an easier way to do this. When you use u sub, you can do it easier so you don't have to plug u back in. On this one, it may not be a whole lot easier, but it does make us have a little fewer steps. So the first thing you need to do when you use u sub on definite integrals is change the bounds. How do you change the bounds? You take your bounds and plug them into u. So we will have the lower bound first. Lower bound will be 0 squared plus 1, which equals 1. And our upper bound will be 2 squared plus 1, which equals 5. I can now rewrite, starting here, right here, I can now rewrite the integral, 1/2 the integral of the lower bound to the upper bound. Now, it does not, you have to keep lower bound as lower bound. So the lower bound may be a larger number with the new u sub. That is okay. You must keep the lower bound math as the lower bound with new u sub, and the upper bound is the upper bound of u to the 5th du. Now, we go and do the integration. 1/12 of u to the 6, which we already know that from here, from 1 to 5. And you'll notice that we have now 1/12 of 5 to the 6 minus 1 to the 6. You'll notice that's exactly what we have right there, with much fewer steps. So that is how we can do definite integrals with u substitution. You change the bounds, it makes your life a lot easier. You don't need to sub back in. If you want to, that's fine, but it does help. Let's look at the second one here. We have the integral of 0 to pi over 8 of sine to the 5th 2x cosine 2x. So we'll let our u be sine of 2x. Our du will be 2 cosine 2x. That's a good thing. We have that there. We're going to change the bounds just to make our lives easier right away. So our upper bound is sine of 0. And our lower bound will be sine of pi over 4. How did I get pi over 4? I multiplied pi over 8 by 2. Sine of 0 is 0. Sine of pi over 4 is square root of 2 over 2. Or 1 over square root of 2, either way. So we now have the integral of 0 to square root of 2 over 2. We did need to divide by 2, so we'll have the 1/2 out in front here to make the du the same. Let's see here, u to the 5th du. And so we will now evaluate 1/2 of u to the 6 over 6 from 0 to square root of 2 over 2. This is 1/12 of square root of 2 over 2 raised to the 6 minus 0 raised to the 6. So this will equal 1/12. Square root of 2 to the 6 is the same thing as saying 2 to the 3rd divided by 2 to the 6. Let me show you why I did that in a minute here. 2 to the 3rd over the 2 to the 6 is, 2 to the 6 is not easy, quick and easy to find, but I know when 2/3 over 2 to the 6 is 1 over 2 cubed, which is multiplied by 1 over 8, and now I'm going to get 1 over 96. You can pause that to try to figure that out or do it in your calculator. But we do have, the changing the bounds makes life a whole lot easier for you to do that. Moving on, we have ln's in this case. So we will again do u of 1 plus e to the x. Du will give us e to the x dx. That's a good thing again. We have it right there. We don't even have to change it or solve for du. We will change our bounds. We get 1 plus e to the 0 and 1 plus e to the ln of 3. E to the 0 is 1, so that will give us 2. E to the ln of 3 is just 3, so we get 1 plus 3, which gives you 4. So the integral of 2 to 4 of u to the 1/2 du. And so we'll just solve it here. U to the 1/2 will get u to the 3 over 2 divided by 3 over 2, which we know is just 2/3. U to the 3/2 from 2 to 4. We can rewrite u to the 3/2 as the square root of u cubed, just as a reminder. So we will have 2/3. Now we can rewrite it as square root of u cubed, as I just said, or square root of u all cubed, and I'll show you why I did that in a minute. Upper bound, 4 square root of 4 cubed minus square root of 2 cubed. So we'll get 2/3. Now square root of 4 is 2 and 2 cubed is 8, so I'm just going to leave it as that. 2 cubed is going to give us 2. That's 2 squared, square root of 2. And I'm going to just leave it as that. Can you? Sure, you can change that. You can make that into 16/3 minus 4/3 square root of 2. But I think it's easier to leave it in that form. Why don't you try and pause the video and try this last question on this page here, and I will come back with the answer. Hopefully this is what you had on your paper. You'll notice that the lower bound is now greater than the upper bound. That is okay when you're changing in u sub. Nothing changed there. Hopefully you remember to bring the negative out in front because du equaled negative x dx. Hopefully you got negative ln of 1, absolute value of 1/4. So let's remember long division. Now, you guys learned long division in elementary school, and then we learned last year that polynomials can be divided by long division. So let's look at this. Let's go 152 divided by, or let's go 162 divided by 5. So long division, you look, 5 cannot go into 1 evenly, so let's go to the next number over, 16. 5 goes into 16 3 times, that's 15. You subtract, get 12. 5 goes into 12 2 times, get 10. You subtract, you get 2, so you get 32 with a remainder of 2. Now what does that remainder of 2 really stand for? Well, let's look at 5 divided by 2. Well, we all know that 5 divided by 2 is 2.5. Well, how do we get that? Well, 2 goes into 5 2 times. You get 4. Subtract that, you get 1. Your remainder is 1. So 5 divided by 2 really equals 2 plus the remainder, which is then divided by 2. 2 plus 1/2 is 2.5. The same idea here. 162 divided by 5 is 32 plus 2 over 5. So 32.4 if you plug that in your calculator. That remainder is added on and divided by the quotient. So in this case, we have x plus 6 divided by x minus 3. So we have x plus 6 divided by x minus 3. How many times, so in this case, when you have polynomials here, we're going to go x, how many times does x go into x? And the answer is 1. 1 times x gives you x, 1 times negative 3 gives you negative 3. You subtract all of that. Negative and negative create a positive, so we're going to get 9. X and x minus x is 0, so you're going to get a remainder of 9. So how do I write this? This is equal to 1 plus 9 over x minus 3, just like I did here. 2 plus 1 divided by 2. This is 1 plus the remainder divided by x minus 3. Let's look at this next one. X cubed divided by 2x squared plus 1. This is really plus 0x squared plus 0x plus 0. We may need that. Again, you look. What do you do to get 2x multiplied by 2x squared to give you x cubed? I need to get 2x squared to look like x cubed. I'm going to get negative 1/2, sorry, not negative, I don't know what I'm thinking, 1/2 x. 1/2 times x squared gives you x cubed. So then I'll multiply 1/2 x by 2x squared and I'll get x cubed. I'll multiply 1/2 x by x to give me 1/2 x. I'm going to subtract that. That's gone. I'm going to get negative 1/2 x plus 0. Now, can 2x squared become, can you multiply anything by 2x squared to give you negative 1/2 x? Sure, you could divide, but we don't want that. So we're going to just say this is our remainder. You can't multiply anything by x squared that's larger than, that's x or larger, to get us negative 1/2 x. So the answer to this question is equal to 1/2 x, and then minus 1/2 x divided by 2x squared plus 1. So now that we know what these are equivalent to, we're going to try and say find the integral. Notice that this first one is not a definite integral, and so we're just finding the integral of this. Well, we already know that x plus 6 times x minus 3 is equivalent to 1 plus 9 over x minus 3, so I can rewrite that and say 1 plus 9 divided by x minus 3 dx. Well, I know the integral of 1 is x, and now I'm going to look and say 9 is just a constant, so I should have probably done this first. I can rewrite this as 1 dx plus 9 integral of 1 over x minus 3 dx. Well, as I just said, the integral of 1 is x. This is going to be plus 9, and we're going back to what we already did on the first page. We know what u is. U is x minus 3, and I think we did a problem extremely similar to this, if not exactly. This one, du is dx. So I'm left with 1 over u, which we know is the ln, the absolute value of u, which is x minus 3. And then you can't forget the plus c. So you need to recognize that when you have 1 over a polynomial in this case, it's the ln of that. And luckily, ln of u, if u is x minus 3, we had no reason to solve for du because we just needed dx, and so we're good to go. Now we have an integral from 0 to 1 in this case. Notice that we have 1/2 x minus 1/2 x over x squared plus 1. Another way to write this is saying 1/2 multiplied by x over 1 times 1 over 2x squared plus 1. And so you'll see that we really have 1/2 times x over 2x squared plus 1. So just so you notice, we can rewrite this to there. So I'm going to rewrite this as the integral of 0 to 1 of 1/2 x dx minus 1/2 the integral from 0 to 1 of x over 2x squared plus 1 dx. And so we do have here the integral of 1/2 x is just 1/2 x squared over 2 from 0 to 1. And so we'll get, in this case, I'm just going to do it out, 1/4 times 1 squared minus 0 squared, and so we're going to get 1/4 in this case. Looking at the next part of this integral, I have minus 1/2 the integral from 0 to 1 of x over 2x squared plus 1. When I have x over 2x squared plus 1, I have to think u sub immediately. Well, if u is going to be our denominator, x squared plus 1, our du will equal 2x dx. 4x dx, what am I thinking? 4x dx. I got to divide by 4 to make it x dx and take care of that. So what I will get here is minus 1/2 times 1/4 from that du over 4. I got to change bounds, almost forgot that. Ooh, yikes, change bounds. So if I do my lower bound to be 0, 0 squared plus 1 is 1. 2 times 1 squared is 2, that's 3, of 1 over u du. So I'm going to get 1/8 of ln of u from 1 to 3. What I know is the ln of the absolute value of u's because I know it's the integral of 1 over u. So I'm going to get ln of 3 minus ln of 1. Well, what is the ln of 1? That goes to 0. And so I'm left with a final answer of 1/4 minus 1/8 ln of the absolute value of 3, which, do you need the absolute value of 3? No, so I could rewrite it with that. That is using integration by long division. So if something does not look nice, you do have to think, maybe I can long divide. If that's not the case, we're going to look at one more that may be the case. We're going to be taking the integral by completing the square. So let's just do a quick overview of how to complete the square. And your favorites, the integrals of inverse trig functions. Always a fun time. So we have the integral of x squared plus 2x plus 2. You can't let u be x squared plus 2x plus 2. That makes no sense because that would be du would be 2x plus 2. That's nowhere to be found here. What does not work? So we have to complete the square. Remember that the idea of completing the square is that we're going to add a number inside of the x squared plus 2x to make that a perfect square. If you add a number on the same side, you have to subtract. So we're going to take our 2, divide it by 2, which is 1, and 1 squared is 1. So I'm going to add a 1 in there to both of them. By doing that, I know this is x plus 1 squared. That's always your b divided by 2, and then plus 1. So that's what this is equivalent to, this denominator. So I'm going to now rewrite the integral of dx over x plus 1 squared plus 1. Now I sit here and say, which one of these is like that? Well, because I have no square root, I know it's tangent. So I'm going to let u equal, remember u is the term with the x, so in this case I know it's flipped, but I'm going to let u be x plus 1, and a to be 1, because this is a u squared does give you x plus 1 squared. Du does equal dx, it's a good thing. So I can now write the integral of du over a squared plus u squared, which we now know that equals 1 over 1 tan inverse of u x plus 1 over 1 plus c. And for the last problem, we see that we have a negative 2x squared minus 8x minus 6. Looks ugly. One of the things that we want to do is take out this negative 2 so we can complete the square. So let's rewrite this as negative 2 parentheses x squared plus 4x plus 3. And then we'll complete the square. know that 4 divided by 2 is 2, and square it, you'll get 4. So we will get x plus 2 quantity squared minus 1. Now notice that we have a negative 2 out in front of all of that. So I can rewrite this as the integral of dx over the square root of negative 2 and the square root of x plus 2 quantity squared minus 1. Now going back here, we can see that this is going to be either secant or sine. Now notice that, as I said, u is the term with the variable that we're taking the integral with respect to. In this case, our u does not have a x in it, so we know that we have to be looking at sine. Now sine has to be a squared minus u squared. Right here we have u squared minus a squared. So this negative, we know we can't have a square root of a negative 2. So therefore we're going to distribute the negative 2 back in and then take the square root of 2 out. So I'm going to rewrite that as dx over, and 1 over the square root of 2, of the square root of, when I distribute the negative 1 back in, I'm going to get 1 minus x plus 2 squared, square root. Now you can see that our a is 1, our u is x plus 2, du is just dx, that's a good thing, and so now I'm going to rewrite that as 1 over the square root of 2 of sine inverse of u, x plus 2, over a, which is 1, plus c. So good for you to see ones that are a little more difficult than what we're used to. Tricky to see, yes, you can take out the negative 2, having to figure that out, but good for you to struggle a little bit with it. For the joke of our day, keep it quick here. What did the calculator say to the student? You can always count on me. Have a good one. See you in class.